Hi everyone, today I will be presenting our paper SentiLog Anomaly Detecting on Parallel File Systems Field Log-Based Sentiment Analysis. This work is from UNC Charlotte and Iowa State University. Here is the outline. First, let's start with the background. Modern HPC systems are growing exponentially. We have many great supercomputers today, such as Fugaku, Summit, Terabyte, and Sierra. A critical part of them is parallel file systems. But as the scale is growing, there are more anomalies in running parallel file system clusters. Fortunately, parallel file system clusters provide a large amount of logs which record the runtime information. We can detect the anomaly from analyzing logs. So the log-based anomaly detection is possible and promising. Before seeing how log-based anomaly detection works, let's first look at what a real log looks like. Here is a snippet of real runtime logs from last year. This is the log content of this log. Some parallel file systems provide the log level in the runtime logs, but Lustre does not. It is not hard to look the source code for the log level. We probably can see many logs share a similar template since they are from a same login statement in source code. We say the logs from the same login statement have the same log index. These two have log index 1. For another unsimilar log, it has a different log index. So logs provide 3 types of information: log index, log level, and log content. So we can detect anomaly by them. Many previous work concentrate on log index, such as DeepLog and invariant mining. DeepLog studied the dependency between logs. For example, it can learn that the log index of 3 and 5 should be 1, 6, or 8. If the new incoming log has another log index, it means there must be an anomaly. For invariant mining, it can learn that the count of 1 equals the count of 3. And this example has 2, 1 and 2, 3. So it is likely to be normal. Another way to detect anomaly is by checking the log level. For example, we have 2 logs here. For some systems, the logs contain their log levels. If not, we can look source code for their log levels. And we can see log 1 is debug, log 2 is error. The error log shows that there is an anomaly. Third way to detect an anomaly is by analyzing the log content, but there is no much work along this direction. A simple method is to search some keywords like error and exception. Some work detects the thematic keywords such as synonyms and antonyms. But can we go further along this direction? These are 3 general ways to do anomaly detection, but for parallel file systems, some methods are not applicable because of 3 challenges. The first challenge is that for parallel file systems, log entries do not share any common identifier to denote their relevance. This identifier often appears in cloud systems. In this example, the 4 logs of HDFS share a same block ID, but the Lustre logs have no such identifier. So in parallel file system, it is difficult to group logs into sessions due to the lack of identifiers. So previous work based on log index is not suitable for parallel file system logs. For example, in systems where logs share a common identifier like HDFS, we can group log into different sessions. For DeepLog, assume we have already learned such dependency from historical data. That is, 6 should be after 3 and 5. For session 1, 6 is after 3 and 5, so it is normal. For session 2, 6 is not after 3 and 5, so there is an anomaly. For invariant mining, assume we have learned such invariant that the count of 1 equals the count of 3. For session 1, the count of 1 and the count of 3 are both 2, so it is normal. For session 2, the count of 1 is less than the count of 3, so there is an anomaly. These log index-based methods work well in systems where logs share a common identifier, but for parallel file systems, there is no such identifier. Here is a typical log index sequence of parallel file systems. Since there is no common identifier, so we are not able to build sessions based on their identifiers. We can only build sessions based on timestamps, but how to choose suitable time windows? For deep log, 6 is after 3 and 5, so this log sequence should be normal. But if we choose a small window, we cannot see 6 after 3 and 5. So it will be predicted as anomaly, which is a false positive. If we choose a large time window, they have too many log indices, which makes it difficult to learn the dependency rules. For invariant mining, the count of 3 is equal to the count of 1, so it should be normal. But the same thing here, we don't know how to choose suitable time windows. If we choose a small one, the count of 3 is not equal to the count of 1. If we choose a large one, it may still violate the invariant rule. So log index-based methods are not applicable. The second challenge is the log level may be inaccurate. The log snippets are from BGFS. We can see the 3 log entries above are simply reporting variable values, but they are labeled as warning or critical instead of normal by developers. And the previous study actually suggested that such variable printing logs were reported as normal level in 95% of the time in multiple open source software. It shows that the log level may be inaccurate, so log level based methods are not suitable. The third challenge is that the label data is difficult to obtain. Many previous works highly rely on the historical label data, but it requires a significant human efforts. For example, here is a runtime log in real cluster. We don't know whether there are anomalies, or even we somehow know there are anomalies. It is hard to determine which lines are associated with anomalies. So the methods depending on label data, such as deep log, are limited in such a scenario. Let's see how SentiLog solves these challenges. For the first challenge, that is difficult to build appropriate sessions based on log index. SentiLog turns to use log content-based methods and propose to use sentiment analysis to understand log content. For the second challenge, SentiLog combines multiple systems login statements to avoid the inaccuracy of a single system. For the third challenge, SentiLog uses login statements in source code, which is naturally labeled. Let's see how we design SentiLog in detail. Here is the overview of SentiLog. We first collect the source codes from many parallel file systems, and then preprocess the raw log statements to build the training data. Then use a BioSTM neural network to train the sentiment model. This model will be applied to runtime logs from real clusters to detect the anomalies. Why do we use sentiment analysis? Below is the real snippets of logs. We can see that the log content not only has symbols and numbers, but also has natural language. More importantly, the natural language shows some sentiments. The anomalies are likely to be associated with negative sentiment log content. So we decide to train a sentiment model to analyze the log content, based on which we can predict whether there are anomalies. But how do we train this sentiment model is a problem. The runtime logs are not suitable because it will take significant human efforts to label the data. Using login statements from a single system source code seems acceptable since they have a natural labels log level, but they may be biased by a developer, so it is not a good choice. Finally, we decide to use log statements from multiple system source code as our training data because they have generic labels. Why these labels from multiple systems are generic? Let's see an example. As we know, some logs have BIOS log level, which we used an orange color to highlight. The fourth log's level is error, but it should be debugged. If our model is trained from this data, when we have a new incoming log which has similar content with the fourth log, the model will predict the new incoming log as anomaly, but actually it is normal. The BIOS log level misleads the model to do the wrong prediction. How can we handle this? If we use another system source code as training data, It probably also has BIOS log level, but not in the same place. If we have more systems as our training data, the probability of being misled by a wrong labeled log gets smaller. That's why we say the label of log statements from multiple system source code is generic. From another perspective to understand this method, more training data of different developers will help the model learn the real sentiments behind the logs more accurately. Then let's see how SentiLog performs. In our evaluation, we utilize 4 real parallel file system logs as training data to train a sentiment model, and an automatic fault injection tool, pfault, to inject fault into running clusters, which are Lustre and BGFS, to collect the testing data. And our metrics are accuracy, precision, recall, and F measure. Since data is imbalanced, we care most about the F measure score. Here is a comparison between SentiLog and DeepLog. Since our SentiLog is based on log content and DeepLog is based on log index, so it can be seen as log content versus log index. For both Lustre and BGFS, SentiLog has a better F measure than DeepLog. Because in parallel file system logs, it is difficult to build sessions based on timestamp, which makes DeepLog not suitable and have many false positives. Here is a comparison between SentiLog and direct lookup. Direct lookup is to simply look up logs corresponding login statement in the source code and use its login level to decide whether it is an anomaly or not. So it can be treated as log content versus log level. We can see SentiLog has a slightly better performance than direct lookup in Lustre, but a significantly better performance than direct lookup in BGFS. It is because Lustre has a more accurate log level than BGFS. Here is a comparison between SentiLog and SentiLog self. SentiLog self is to train SentiLog using only the target parallel file system instead of mixed parallel file system. It can be treated as training on multiple source codes versus training on single source code. It shows that using multiple source codes as training data can improve the performance clearly. In conclusion, first, we propose to use sentimental analysis to understand log contents and detect the anomaly and shows its effectiveness. Second, we propose to train sentimental model using source code from multiple systems to solve the issue of lack of training data to avoid bias of each system. For the future work, we decided to explore the possibility to consider more features besides the log statement description, and also conduct more experiments to validate and quantify the generic sentiment across different software. That's all. If you have any questions, please feel free to ask. Thank you.